And sweet. Okay, so this is where we were last week, talking about stress strain curves, how the physical grains of the metal or material. This just happens to be a metal because they're relatively convenient for us. How they can affect how a material strains in response to stress. Today, as I said, we're going to be talking a little bit more about other ways that materials respond to strain, or other ways that they can be strained. The first two guys we're not going to spend as much time on, slip and creep. What you can essentially think of these two as, creep, I'm going to go in reverse, which call reverse order. Think of if you've ever had just like a bucket of water hanging on a rope or hanging on a wire. Like my grandmother, she has this ornament hanging by a door, and it's just this thing that's hanging on a curved piece of brass wire, like this. And over time, it droops a little bit lower and a little bit lower and a little bit lower. I mean, nothing's pulling down more over time. So you'd think that like there wouldn't be any force that would be making the wire bend more. But this is what's called creep. It's time-dependent strain. You have you have a constant force, and even though the stress is the same, over time, the amount of strain for that loading will gradually increase. That's the idea of creep. Slip is kind of the opposite thing. If you think of these grains, and you apply a force, and you apply a force to them, just like we've been talking for the last week. They're going to strain. These individual grains are going to move or deform relative to one another. That's slip. Relatively straight, which is called relatively straightforward. It's what we've been dealing with all week. But they're not as interesting as the other three. So let's start with fatigue. So how do I want to say this? Fatigue comes from a cyclic loading. So it's called a cyclic loading would be that, I'll get to this in a second because it's a really good example of it. But say that I had, my calibration is off. So say that I had a beam and it's rotating, all right? And how do I want to say this? Say that I have a gear on this. Wow, my calibration is really off. And I'm pressing down on it. I'm pressing down on it. So there's always going to be a force pressing down on this beam. But say that I have like a point here. If I look at that point, okay, stay together now. Okay, so if I'm pressing down and this beam is rotating, am I always pressing down at the same physical point on the beam? No, right? Hey, that point's traveling around. So at one point it'll see whatever stress I'm pushing down with, and by the time it's down here, is it going to feel anything? Is it going to feel hold me pushing down anymore? Yes, no, maybe. Like if you had a finger right here, and say this is a perfectly rigid bar, could you feel me pressing down? If you want to actually feel it, feel free. So like, can you feel me pressing down on this? No. Right. So here you feel, so a point here feels no stress or very, very little stress. Up here it experiences very, very high stress. So as this bar is spinning, as this part is spinning, it goes from high, which call it Poisson, it goes from high to low to high to low to high to low, high to low stress all the time. And that causes what is called fatigue. It's a cyclic loading, so it happens in so it happens in cycles. Guess what? There we go. Go over here. There we go. So it happens in cycles. It's an oscillating loading. So, for example, of say, this is a a piece of jointed drill pipe that they use for horizontal drilling. It bends, right? Yeah, you have what's called sections that are curved, and say that at the point where it's bent at a maximum, it's touching off on the rock. That creates some load, right? If I'm bending and I'm pressing out against something, like kind of like if I have all these pieces of paper and I'm bending it out, if you could push on them, please. Thank you. Like that bend has to resist a load. And if it's spinning, I have an oscillating load, right? It goes from a lot to zero, a lot to zero, a lot to zero, a lot to zero. So this is a perfect example of fatigue. But why in the world do we care, right? I mean, at the end of the day, it's still a load. It's still stress. And so long as we have designed for whatever the ultimate, so long as we've picked the material correctly for its maximum stress, we said, okay, so this is a load that we're going to see. Let's make sure we design the material so that it can accommodate the load. Everything should be fine, right? That's everything that we've done. However, the trick with fatigue is that people have found that things start to fail early. One example would be, if you remember in like the mid-2000s, Southwest had some major problems with fatigue in the skin of its 737s. You can just kind of see it, but this tear is along a seam where this skin was joined into which called the body of the aircraft. And over time, even though it never experienced loads that would ordinarily make that skin fail, I mean, a 5-foot, 6-foot section this way, I think of like 15 feet that way, ripped off of the plane mid flight. So if this was due to fatigue, and fatigue contributed to the failure, what were the cyclic loads on that skin?
Air pressure.
Air pressure. Why?
It's high on the ground and low up in the sky.
Yes, that was an excellent example there. Yes, yeah. On the ground, you're at what you call about 1 atmosphere pressure. The inside of the aircraft varies in pressure for when you're flying. The inside of these things is typically pressurized what you normally feel at 8,000 feet. So the inside's always going to be typically going to be some higher pressure than what you experience outside until you start coming down, and then it's a higher pressure outside than inside again. So you have this oscillating load from low to high, low to high, low to high, low to high, and it results in fatigue. Now, really, this is actually a really complex topic, but the gist of why this occurs can kind of be explained by something called an SN diagram. The idea is that you have some applied stress and you have some number of cycles that the load's being applied over. This would be completely reverse cycles. So it'd be going from, say, positive 100 pounds pressing down on the top to feeling negative 100 pounds on the bottom. That's a completely reversed load. And the kind of wacky thing is, I mean, the more cycles that you go, the lower the what's called the lower the failure point of these various materials are. And what's called, and you guys have probably seen this, like if you have a what's called, like if you have the top of a soda can and you just like wiggle that button back and forth and back and forth and back and forth, it'll eventually break, right? That's this. You're putting it through a number of cycles, and you're bringing this this ultimate stress down to the point where it's the same or less than the force that you're pulling on that little button and with. So that's basics of fatigue. Full treatment of it's kind of beyond us right now, but it's a good thing to be aware of. Any questions on it? Cool. All right. So thermal stress. This is where it gets a little bit more interesting. But I'm going to pause here because I really need to recalibrate this board. Else, this is not going to work out well because I need to draw. Okay, let's try this one. Let's try this one more time, and hopefully it'll work. So thermal stress. You guys are come on, you can do it. There we go. Okay, so you guys have probably you guys probably know already that like if you heat something up, it gets bigger, right? Thermal expansion. Like that's why in sidewalks we have the cuts every 3 feet, 3.5 feet or so, and it's filled with some sort of like a caulk hook. It's to help alleviate thermal stresses by giving those blocks of cement somewhere to expand. It's called, there's also kind of intense concern if you have like a spatial re-entering Earth's atmosphere. There's a lot of work done into making sure that as the spacecraft expands, you're not going to break anything. But let's back up and say why. Okay, so there we go. So thermal strain is directly related to something called the coefficient of thermal expansion. This is essentially an amount of strain per increase in temperature for that material experiences. So, for example, copper, some forms of copper have a coefficient of thermal expansion of 17 times 10 to the negative 6th strains per degree C. Okay? So for every degree C, you get 17 microstrains, if you will, of strain. We cool with the crazy units of strain? Yes? No? Maybe? Okay. I see at least a couple of heads nodding. Okay. So that's something that we have a nice straightforward relationship here if you want to figure out how much thermal strain we have. So if I throw a given temperature difference and it's at a piece of material, how much it's going to change in size or shape. For right now, we're just going to look at length. We're going to look at other things later on. But this isn't necessarily stress. What's called thing about thermal strain is that by itself it doesn't cause stress because it's just the material changing shape. There aren't any forces involved with this. So like if I heated up this piece of copper here and say it's part of some motor windings and the motor's getting really hot, it heats up by 90 degrees C, this is going to change in length. But it's not necessarily going to have any stresses acting on it because it's just heating up. The material is physically growing. However, if I constrain it and I stop it from expanding, that's when we start seeing the stress because it wants to expand, but it can't. So the question is, how in the world do we compute that? So let's have a look. Oh, I hope this doesn't crash. Thank you, Lord. Okay, so I my bar copper. Even if I know that I'm going to constrain it in some way, I'm going to start by considering it just free. At least I can say on one side. So it's just going to expand in this direction. All right? So if I heat it up by 90 degrees C, what is the strain going to be? The strain is alpha delta T. Thermal strain anyhow. What's my strain?
1.53 millimeters.
That's a deformation. How much strain do I have?
17. That many strains.
Okay, so you have 17 microstrains per degree C, right? That's this. Multiply that by 90 degrees C. I end up with units of microstrains. What's the value associated with that? 17. Say again? Nope. Okay, so if I do my unit analysis here, this is units of strain of 17 times 10 to the negative 6 strains per degree C. Because it's times 10 to the negative 6, 10 to the negative 6 is the same thing as a micro. So I can rewrite this coefficient of thermal expansion as 17 microstrains per degree C, right? So that's what I have here. My change in temperature is 90 degrees C. Degrees C cancel out. I'm left with units of microstrains. The value that goes here, 17 microstrains, call it like the number that goes here, is 17 times 90, which is what? Say again? 1,530? Great. Okay. Great. So 1,530 microstrains. Awesome. Now, make sure that, let's make some more room. Okay, so strain equals 1,530 microstrains. Great. All right. Now, if we just left it free to expand like that, that would be our strain. We could find an ensuing deformation by multiplying that by feet, right? So this is like, if I wrote this in strains again, this would be like 1.53. If I can write 1, 2, 3, yeah. 1.53 times 10 to the negative third strains. Multiply this by feet by a 1 foot length, right? Because deformation is strain times the original length. I get 1.53 times 10 to the negative third feet of total length change. However, we get into a little bit of a sticky wicket here because we said we want to see what stress we get if both sides are constrained. And in the problem that we just did, the material really expanded to be a little bit longer, right? So it's beyond where it would be if it was totally constrained. But here but this is fine. We can apply what's called the principle of superposition, kind of like we did before, which means that we're going to break the problem up into multiple chunks, and if we essentially add up all the chunks, we'll get the answer that we want, and we can do it for what's called problems like this. Anything I can say if it's a linear problem, and I'll explain what that means later on. So how do we solve? So how do we finish this out? So we have some deformation here, but we have some strain that's associated with that. But like we've said, we want to know how much stress is generated if that strain is what? If both sides are constrained to the original length, to stay at the original length of the part, how much strain actually occurred if this thing cannot move? Yeah? Zero? Anyone else for zero? What do you think, Frank? You look very quizzical. What do you think that the strain is? If this part could not change length at all. Say again? Okay, so your intuition is correct. The cross section should change. We're going to ignore that for right now, but you are right. Let's just look at the longitudinal strain, if you will, the strain in the long direction. So the one that it's constrained in. If both sides are constrained, so the thing cannot grow any larger, what is the total strain here? Got one vote for zero. Zero. Why? Why? Okay. Yeah. So if I look at the definition of strain is deformation over original length, right? If the deformation in any given direction is zero, it means that the strain is also zero. So in this case, let me erase some of this. So in this case, if I've constrained both my ends, it means that my actual strain is zero. My deformations are zero. So how much in a sense, I can think of this problem as, okay, the bar, I've ignored this side here, the bar's expanded. Now I need to shove it back to fit in whatever box that I've originally told it to be in. In this case, that box has a length of 1 foot. So the strain, I need to push it back to zero strain, which means I need to push it back by this much, right? So that means I can say, well, if stress equals Young's modulus times strain, I'm trying to compress the material by 1.53 times 10 to the negative third strains, and say my Young's modulus is like this stuff's relatively soft, so like 70 megapascals. And I get a stress. Yes.
Does Young's modulus ever change with temperature?
Depending on the material. Yeah. It also depends on how much temperature swing you're looking at. Like if we're looking near the melting point, then yeah, it's going to start doing weird crap. But other than that, you can generally take it as a constant. Generally speaking, very generally speaking. Do we have any questions on thermal expansion, thermal stresses? Is this clearer than mud? Okay, cool. All right. And you can have multiple things, of course, undergoing thermal strain at the same time. Just like a couple weeks ago, maybe one week ago, we had a problem with a bunch of pieces of rebar and one block of cement, and they were all stretching at the same rate because they all had to stretch with the cement. You could have get a piece of rebar there being heated at the same time, and it's causing thermal stresses in the cement and all that. So you can play this game a couple different ways. Okay, last stop, Poisson's effect. This is where it gets fun. Poisson's effect is kind of what you've always seen when you were bored in school and you started stretching your eraser. So you take it, you pull it, you push it, you pull it, you push it, and if you look really close, and if you look really closely at it, what can you see about the top and the bottom as I pull it and push it together? Can you see anything that's changing with them? Yeah, so when I pull this guy, it actually, it's called the top and the bottom of the eraser actually get closer to one another. And if I push it, the opposite occurs. They get further away from each other. It's called based on it's called the stress that I incur in one direction actually causes a strain perpendicular to it, and that's what's called Poisson's effect, and it's quantified via something called Poisson's ratio, which is a ratio of the strain in one direction, say something like sigma epsilon xx, so the strain in x, relating that to a corresponding strain in y. So if I wrote this out into, so if I wrote this out and said, okay, I have some stress in x, and from that I can find some strain in my x direction. That's an E, I promise. I can then say, well, Poisson's ratio by using Poisson's ratio, I can find out what fraction of that stress in the x direction gets supplied to the y direction. Okay, you happy with that? Sweet. Okay. So where the crap does this come from? See if we can tie this together. So Poisson's ratio is generally constant. However, depending on material, its value can depend on direction, temperature, other material properties. We are looking at mostly what are called isotropic materials. Isotropic materials means that the material properties are constant in all directions. No matter which way you're pulling on it, it'll act the same way in terms of strength, in terms of Young's modulus, in terms of modulus of rigidity, in terms of Poisson's ratio, in terms of coefficient of thermal expansion. All these things will be the same. And so this be materials like most plastics are isotropic materials. Steels are isotropic materials. Aluminum is like pretty much any metal is an isotropic material. Most homogeneous things. So like this is a big block of this desktop is a big block of resin. It's a big block of glue, essentially, that they formed in a certain shape. It's an isotropic material. However, when we get to things that are not homogeneous, say like a block of concrete that has rebar in it isn't homogeneous. It has these pieces of steel running in a particular direction. along it. So it's stronger and stiffer running along the rebar than across the rebar. You might think that if you like drew a line through the material, there'd be less steel in a certain direction than in another direction. So direction with more steel in it's probably going to be stronger, right? That which call reinforced concrete's not an isotropic material. Fabric's not an isotropic material. Composites are definitely not isotropic materials. They're a whole thing by themselves. And all of those things are very, very difficult to analyze. So we're going to start out with isotropic stuff. And these relations here describe how isotropic materials strain. This is in three space. So there are three normal stresses there, three normal strains. They're all related to each other by some, in this case, constant Poisson's ratio and constant Young's modulus. So that's kind of like the basics of that's like the basic setup for isotropic materials, if we're ignoring thermal strain. If you wanted to add that in, as you'll see later on, it'll just be a little alpha delta t tacked on to the end, because it's not related to stress. But again, let's get back to the point. Where does this come? Where does this come from? And we'll get there. We're getting closer. I just talked about some of this. This kind of says it in math, if you will, in terms of the different kinds of materials. But let's look down at this guy. Because we have an isotropic material, we can work the numbers. We can come out with some pretty neat little relationships like this, which relates Young's modulus, modulus of rigidity, and Poisson's ratio. So we can, for an isotropic material, we can approximate one from the other, which is cool. Does this relation infer any limits on Poisson's ratio? Can't be more than one?
Less than one? There's a 1 in there.
There is a 1 in there. Why less or why greater or why? Okay. Any other thoughts?
It can't be less than 0.
Can't be less than 0. Why?
Because then that things would happen. It would be like one of those things where you compress and it expands.
Yes, it would be like one of those things where you compress it and then expand. So if Poisson's ratio is less than 0, it'd be negative. It means that if I pushed in, if I pulled out, that ratio, instead of contracting, would expand, which would be weird. And some materials actually do that. It's kind of like a reverse Chinese finger trap. You can think of a regular Chinese finger trap. You pull it, it crunches down as being a positive Poisson's ratio, and if you did the opposite, you pulled it and expanded, it would be a negative Poisson's ratio. And there are actually materials that do that. But let's look at it from this point of view. So this essentially is the ratio of Young's modulus to modulus of rigidity, right? What if the right-hand side, what if all this equaled 0? What would the value of Young's modulus be? 0, right. Does that make any sense? Correct. So one limitation as to the value of Poisson's ratio must be that it must be greater than -1. That's got to be one. That's got to be one end, because if it's less than -1, it means that we have like negative stiffnesses, which means that like they're sitting there and they blow up, which doesn't make any sense. And materials don't do that. So that's one end. The other end is it can't be greater than 0.5. So the limits on Poisson's ratio essentially that. The 0.5 is to satisfy to satisfy limits on on differences between Young's modulus and the modulus of rigidity, I believe. I'm forgetting off out of hand, but that's the reason why there is an upper limit. What does that look like? So like rubber, if you can think of things like that eraser that I had, it is a very pronounced Poisson's effect, right? Like I can strain it and I can see the change, which is odd, right? Because normally, like if I pull on a piece of steel, like it's experiencing stress, but I sure can't see anything, right? Rubber has a very pronounced Poisson's effect, so it has a value of 0.5. If its Poisson's ratio is about 0.5. Something like steel is like about 0.3. Cork is 0, more or less. Materials that have a negative Poisson's ratio. Hang on, I just want to show this video because it's so weird. There has been a great people are really interested in finding these things out. So a lot of people have spent time in making materials like this. So if I roll this thing up, pick it up and pull on it, it actually grows because of how that lattice has been put together. So you have to put a lot of work into making a material like that, but it's not outside the realm of reason. If you think of the things that they've been doing with like carbon, which is called like carbon nanotubes, where they can, or with composites, where you can actually change how the fibers are aligned inside of a material, you can actually make something that does this, which would be neat. Say if I had like say a pin that I never wanted to pull out of a hole, right? I could have it so that it expands when you try to pull it out, and it locks itself in with friction. Or I want to have a brace that gives more support when it flexes, because it'll actually grow. So you can do some kind of neat stuff with it. Yeah.
So it can be equal to -1, or is it just less than?
It can be greater than equal to. It can be you're right. This should be greater than -1 or less than equal to, or less than 0.5. Rubber is really close to 0.5. It's like 0.4999. Yeah, sorry. Yeah, it wouldn't make any sense if it was equal to. Okay. But we still haven't really answered where the crap does this come from. It comes from this nasty, messy, crazy thing. Don't worry about this too much. This is more or less for like shock factor. This is more or less for shock factor. If you take linear algebra, this will make more sense. The general idea is that this describes how materials work. It's a more compact way of stating those relations that we had earlier, those three equations for strain. This is the same thing, but it includes shear strain, shear stress, normal stress for an orthotropic material. So you have a different Poisson's ratio and modulus of elasticity in all directions. However, we don't care about that. So in 2D, for isotropic materials, it looks like this, where this little guy here is your thermal strain. And if I wrote that out in regular equation form, it would look like this. Okay, cool. Yeah, that's all I wanted to say about that. As before, we said that thermal strain is not directly related to stress. We can kind of pick up on that here. If we wanted to solve the same problem we did before that we solved by superposition, and we wanted to think of it more mathematically, we could say, what if I heated up that bar of copper by a certain amount. I constrained it to have 0 strain longitudinally. What stresses are evolved? I could ask, I could solve that sort of equation here too, with more math and less concept. But that's the basic idea. Almost out of time. Can I do that? I don't want to get into that. All right. Well, we'll just do a quick example and call it a day. So let's go back to that bar of copper that I had before. So constrained, constrained delta T equals 90 degrees C. Wow, I can't draw an alpha. Alpha equals 17 times 10 to the negative 6th strains per degree C. So if I heat this up, I get what? 1.53 times 10 to the negative 6th. No, sorry. 0.53 times 10 to the negative 3rd strains in X and Y, right? Because what's called the coefficient of thermal expansion is the same in any direction on this material. So for a given delta T, a given alpha of the same strain in all directions. If this dimension is 1 foot and this dimension is, say, 1 inch, I can find some sort of which I can find into my deformation in the y direction just by the definition of strain. I'm going to run out of time both before I finish this. Where I wanted to go is if I have to constrain this to 1 foot. So going back to the we found out how much stress that strain would generate. The question would be how much additional strain do I see in the y direction because I'm constraining this. And actually this will be a lot faster than I thought. So we could go through our 2D strain equations. We could find it like that, or another way that we could look at it is that we know what the strain is in X. That which called that's causing this stress. Correct? We know that we've constrained this bar to 0 strain. So even though it wants to strain by this amount, it has to be 0. So if we know Poisson's ratio for the material, we know that would be the ratio of strain in Y over strain in X. So if we wanted to find the additional strain in Y caused by this boundary condition, just be strain X times Poisson's ratio. That gives us the additional. If we add that to our the original strain in the y direction that's caused by the thermal stress, that by the thermal strain, that gives us the total strain in the y in the y direction. Does that make any sense? Essentially, we're just adding together all the different effects that we're seeing here. Or if we went back to our equations, we found we could say that we found the thermal strain. There wasn't any of this, and then we just found the other contribution to the strain in the y direction that's due to the strain in the x direction, which is just sigma xx over E, or strain in x. We all on board with that? Cool. If you have any questions, happy to take them. If you have any specific problems you want to bring to recitation tomorrow, glad to play with them then, because went through the examples I kind of wanted to. That's all I got. Thanks for stopping by.